this Unity tutorial, I'm going to show you how to have Unity make a maze. First, I'm going to press play so you could see this maze generating algorithm in action.
Completed.
Basically, first it just made a grid. It picked a random grid cell, and then it moved from that random grid cell to another cell, a neighboring cell that had not been visited. And between those two cells, it would remove the wall. Then it'd pick again another random cell unvisited and remove the wall. If it ever came to a point where there were no unvisited cells next to it, it would back it up until it'd find the unvisited cell and then go in. I'm just going to slow it down a little bit. 1 second for each cell. Okay, and I press play. So as you can see, the first thing is it made a grid of cells. All the unvisited cells have this smoky color. Green, green, and between the cells that it moves, it removes the wall. Okay. And we still have green, there's still cells around it. But sooner or later, as it randomly moves around, it's not going to have a nearby cell that is unvisited. Like there. Backs up, then it finds one again. Oh. Has to back up now. And it's going to have to back up quite a bit because all these cells have been visited except this one. It takes it. In order for my maze algorithm to work, I need something called a maze cell prefab. I'm going to show you how to make the maze cell prefab. Just for reference, I'm going to add a floor here. So that would be a cube that I'll just spread out. Okay. Now when I start to make my maze cell prefab, I'm going to start off with a cube. And I'm going to give it a transparent material so I could basically see through this. So this is going to be my prefab that I'm showing you how to make. Just add the 4 walls by adding cubes for each wall. So let's say that this is one of the walls and the width is 0.1, and I just have to move this one over to the edge of my cube. I'm using a cube to measure how far over I have to go. So that would be about minus 0.45 for the left wall. Right, so this would be my left wall left. Then easily I could make the right wall by copying that. Wall right. And changing from minus 4.5 to positive 4.5 for my front and back. So my front wall, that's going to be, instead of the x-axis that I change, I'm going to change the z-axis for front and back to 0.1. And then I will do 0.45 to move it forward on the Z, and that could be my wall forward. Oops, spelled that wrong. No problem. I'm gonna make a copy of that for my wall back. Rename wall back. Bam. And the wall back just moves back until, what's that? Minus 0.45. Now I have the 4 walls. And the front wall, I'm just going to drag and drop this texture on so I know which direction is front when I'm looking at this at all times. There goes F. I also want my maze cells to have their own floor. That way, whatever size the person who makes the maze, there's always a floor for the maze. So I'm just going to add another cube. And this one is going to have a height of 0.1. And I'll just move on the y-axis. I'm moving down, so minus 0.45. and I'll give that the name floor. Okay. Then I'll just put texture on there. Good. All right. And the only other thing I would have to do is add the script that I wrote for it right here to it. And the script, so that I could do operations to each of its pieces. It just wants to know what all the pieces are, so I could drag on the left, the right, the forward wall, the back wall, and the floor. Now let me take a look at the script. So let's see. Here's all those inspector variables. And then there's a private variable to say if the cell has been visited or not. We have to know if the cell is visited or not because the algorithm depends on that. It only visits unvisited cells. So once a cell gets marked visited, it can't be used in the algorithm anymore. All right. I have this little region here. I pegged it helper. And what's in here is an enumeration. So I enumerated the 4 wall types. And if there's no type known at the point, then there's also one type called undefined. So the only function here that really matters is this one, remove wall. The algorithm will call the cell and tell it to remove a particular wall. And the way it specifies which wall is with the enumeration for wall. So if it's wall left, then I'll set active of wall left to false. And the same thing with right, forward, and back. So this function here works on a game object, dot, set active, and then you can say true or false. So what does set active do? Look over here. Say that I wanted wall left, that's this wall right here, to remove itself from my cell. Now I don't really have to remove the game object. I don't have to say delete in code. I could just pick that wall and check this check mark off, and then that wall would be removed. And same thing if I did another wall like the back wall, remove. So it's still there in my object, but I turned it off. And that's what the remove wall function is going to do for us. And that's why we need it here in our maze cell script, so that when the maze algorithm is putting 2 cells together, it could remove the walls between them. What I manually want to do now is show you how the maze algorithm is going to work. So first thing I'm going to do is add some cells. I'm manually putting some cells here. I'll make it a 3x3. Okay, and one more. 3. And the maze algorithm is going to make all the maze cells a child of maze. So I'll just put them as a child of maze. Okay, so this is the first one. This is the bottom left, top right. And this one is the center. The first thing the maze cell algorithm is going to do, it's going to use the camera and place it over the center cell, whatever it is of the maze, the center cell. So in this very small maze, it would be this one. And then from the center cell, it's going to take the camera that it positioned there, and it's going to point the camera to point down at the maze. Then the third step is it will move the camera up on the y-axis until the camera could see the corners of the maze. And the last step is it will move the camera up one more notch so that there's a little bit of an outline frame of space in the maze. That would be the maze algorithm's first thing, is making the grid and positioning the camera. The second thing the maze algorithm will do is it'll pick a random cell of the maze, Let's say it picks this one. This cell would be the current cell, and then it picks a random neighbor. So for this cell over here, the random neighbors that are possible are either this cell or this cell to be the next cell. So let's say it picks this cell to be the next cell. Okay, that means in our next cell, we'd have to remove the back wall. And in the current cell, we'd have to remove the forward wall. Boom. Now this becomes our current cell. When this is our current cell, the algorithm will pick a new random neighbor. So this cell has 3 possible neighbors. It could go forward, it could go right, and it could go down, but since down was already visited, it won't go down. It will only pick between forward and right. And let's say it picks the right cell here to be the next cell, the right neighbor. That means which walls do we have to remove now? In the next neighbor cell, we have to remove the left wall. And in the current cell, we'd have to remove the right wall. Okay. And then let's say we go now to that this becomes our current cell, and this is our next cell. So in this next cell, let's just say it again. What we're going to remove is the back wall. And in the current cell, we'll remove the front wall. And then let's say that this becomes our current, and the next cell happens to become this one. Just one more time with removing the walls that are shared. I will have to remove the right wall here. That's my next cell. And in the current cell, I'll have to remove the left wall. Now we're at this cell in the algorithm. And the possible neighbors are here and here, but they've both been visited. So I can't pick either of them. So what the algorithm will do, it will look back to the cell it came from here. And now it'll check again for a neighbor. So now the neighbors it has are here, here, and here. This is the only one that's not visited. So now the algorithm will move forward again, and this will become the next cell. And it will do the thing where it removes the walls, which over here would be the left wall. And in the current cell, it'll be the right wall. Then again, nowhere to visit, it moved down. So every time the algorithm runs, it's going to look where it is, sees if there's a neighbor. If there's no neighbor, then it will move backwards and see if there's a neighbor. So here there's 2 neighbors it could pick from. And if there's a neighbor it could pick from, then the algorithm will move forward. Now for probably the hardest part of this tutorial, explaining the maze generating code. So the script needs to know what the maze cell is. So I drag and drop it from the assets folder onto there. And the script needs to know what the camera is. So from my scene, I would drag and drop camera onto there. The algorithm allows us to type in the size X and the size Z of the maze. To explain the linked list, I kind of have a picture I made here where a link item has information about the maze cell, and then it has a pointer to whatever the link item before it was, and it has a pointer to whatever the link item after it will be. So on the first link item, my start cell, there really is no previous link item, so that will just be null. And I could have as many linked items as I want. On the last link item in my list, the next is going to be null. It never gets set. So the benefit of the linked list, in the list I can go forward and backward and get all the other links. So in the maze, when I have to travel backwards from the cell that I am, say if this is my current cell, and I have to travel backwards to this cell, to the previous cell. With a linked list structure, I could just use the previous link item and go back. Recursion, and in simplest form, I have some function that calls my recursive function. So here in this example, there's a variable number, it equals 10. And then I call my recursive function that's here in orange. The recursive function does something to the number, it subtracts it, and then the number, if it's still greater than 0, I call the recursive function again. If number's finally 0, I have an out, and the recursion stops. I'll come back to my start function. I think the best thing is going to be when you have the code and you're able to run it yourself. So what I'm going to do is I'm just going to expand everything here and scroll through the script so that you could have a chance to copy it from the YouTube video. And if you don't want to copy it from the YouTube video, you can go to omarvision.com and look up the tutorial there on my website, and there I'll have the source code. So anyway, here's at the top, here's a new neighbor case. Then I have a new neighbor to the left, right, forward, or back. Then I have my coordinate class, which just holds information for a May cell, like its XZ position, and if what is it, the neighbor to the left, the right, forward, or backward. And in this neighbor cell, what is the wall that I have to remove in this cell itself, and what is the wall I have to remove in the parent to the cell. And you see by default that x and z equal -1. So if I want to make sure that the cell has been set and it's not equal to -1, that's what this property is. Public bool is set. That's a property, and it just checks to make sure that x and z are not -1. Then there's a constructor that takes x and z, a constructor that takes x and z, and what kind of neighbor this cell is going to be. And here's the logic to say whether I'm going to remove the right or the left and the right, the back and the forward of the current and the parent cell. Then this is a constructor that just takes another coordinate class object and makes a copy. This structure represents my linked list. An array, you start at one place and you could move through the indexes of it. A linked list, each item points to the next and the previous. So link coord is a linked list of these coordinate class objects. So first I have the current coordinate object, and then I have a pointer to the link coord of the previous and a link coord of the next. And I have a constructor that takes a coordinate. Okay, these are all the things up in my helper. Now these are some public variables that you saw inside of in the inspector. I have the maze cell prefab, the camera, and the size, the maze generator script right here. 1, 2, 3, and 4. 1, 2, 3, and 4. I have a 2x2 array of maze cells as they're instantiated into the scene. And if I have one link in my linked list of coordinates, then I have a link to everything. Now the start function, here you can copy that, and make grid of cells. Let's see, it's going off the screen a little bit. You can copy that. Then generate maze, which I explained somewhat. And script sort of is just so I don't have to type all this code to get the maze cell script every time I want to do something to the maze cell. And then random neighbor. I have a little comment explaining the cases of neighbors, and that plus, minus, minus, and plus the direction that the neighbor's in. So here first we try to find out the case of the current cell. What's the neighbor case of the current cell? So I look at the current cell and I determine from its z and its x coordinate what type of neighbor case it is. So here Z max is like the top row. And then I have X all the way to the right, X in the middle, and X all the way to the left. Then these are Z rows that are anywhere from in the middle section. M5 is probably the most popular case for all the cells, M5. Then when Z is at the bottom, boom, boom, boom. So at this point, I'll have all my, I'll know what the neighbor case is. It will be set. Now, based on the neighbor case, I could find a random neighbor. So I just have a big switch statement. And I made some functions to call out to, so this function wouldn't get too long. The next object, the next neighbor is created. Now I just return next to the caller. These are the get next fors. So here's get next for T1. This is the first one, and I put some comments. These are the possible neighbors. I filter for just the unvisited ones. Then I pick a neighbor from the unvisited using random range. Then I remove the adjoining walls. This is for case T2. Top row in the middle somewhere. There's 3 possibilities for neighbors. T3, top row all the way to the right. M4. Now we're in some middle row of Z, but we're all the way on the left. M5. We're somewhere in the middle of the maze. This is where we have the most possibility of neighbors. 1, 2, 3, 4. M6. We're somewhere in the middle of the maze, but we're shoved over to the right on a cell. B7. We're at the bottom row to the left. B8. We're at the bottom row in the middle somewhere. And B9. We're at the bottom row all the way to the right. When I'm going through the algorithm, the recursion, I need to check to see if there's any unvisited cells. When I've reached a point that there are no more unvisited cells left, I know the generate maze algorithm is complete. This function checks to see the whole 2x2 array to see if any of them have is visited equal to false. And this last function is the center high camera. Basically finds the bottom left maze cell, a cell in the center or close to the center, just by dividing the sides by 2, and the top right maze cell. So this is just a little representation here in the comment of the center maze cell, the bottom left, and the top right. First thing you do is you position the camera dead center over the XX and just raise it up on the Y by 1 pixel and have the camera look at XX. That way the camera is looking down at the maze. Note over here I have a loop. I'm using a loop, so no matter what, it's going to stop at some point. So I figure if I add size X and size Z, that'll be enough chances that I move the camera up. So I move the camera up a notch at a time by a unit of 1. And I move it in world space, not camera space, because since the camera's rotated, I can't tell which way is up anymore, but I do want it to move up in the scene. So I use space.world. And I pick a point. I pick the bottom left cell. I pick the bottom left cell's point. And I see, with this conversion function on the camera, if that point is on the screen. If that point is in the viewport. If it's in the viewport, in view. Otherwise, the point could be out here. So if it's in the viewport, then on-screen will equal true from this little Boolean statement. That means my whole maze is visible at this point. The camera has moved up so that the whole maze is visible. Then I just move the camera up a little bit more so that the maze view has a little bit of a frame around it where you're not just seeing it to the corners of the cells, you have a little bit of space around it. Just one more bump. And that does the camera position. So that's the whole script code. You can look for it on morevision.com. And all right, what should I do as the last thing here? I'm just going to run the algorithm just one more time. So first let me put this back the way it was. These were the cells I added in manually. I'm just going to remove them. And this floor I added in for the demonstration purposes. I'm going to remove it. So this is what I need to start off with. Cancel. File, save. Save my scene. This is what I start off with. And I have a 10 by 10 maze. You guys have seen that in action. So let's do a bigger maze. Let's do a maze of 25 by 20. How about that? I mean, you can go even bigger, but let's do 25 by 20. What am I doing? And press play. Boom. And you can see the camera raises up as high enough as it can. And as children of the maze empty object, it puts all the cells, because otherwise the hierarchy window would really get flooded. Let's try even bigger. Let's try 40 by 40. And run that. Boom. So the maze can get bigger and bigger, any size, just by these variables here. And this is the camera view in the game mode because the camera moved up. And if I look at it from scene view, I guess you could use a first-person controller and try to walk through this maze and find your way through. Or you could play a game where you're just looking at it from top down. All right, enjoy.